Acquired archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. Tonight, you will listen to the summary of the story we are entering. A crew leaves the familiar light of the inner system, carrying instruments, patient procedures, and a ship built to measure time itself. They travel toward a dark, quiet black hole, not as a myth, but as a place of real gravity. Along the way, the universe begins to do something strange and measurable. Their ship clock ticks at one rate. Far from the gravity well, Earth time ticks a little faster. The difference starts as seconds, then minutes, and it becomes a gentle thread running through the whole mission. This is a journey into a black hole, Chapter 1, the briefing that lasted a year. If you are listening in bed, or on a late train, or in a quiet room with one small light left on, let your breathing soften. In this archive, we do not rush. We gather details the way starlight gathers in a mirror, slowly, patiently, until an image appears. The mission was never announced with fireworks. It began as a spreadsheet in an orbital engineering office, a set of margins that did not quite close, a mass budget that refused to stay within a launch manifest. It began with a question that sounded simple in a meeting room and felt enormous in the body. Can a crude probe approach a black hole close enough to test strong gravity and return data that will still make sense back home without turning the crew into a story of loss? The black hole was not a monster. It was a destination, a compact object in a quiet part of the Milky Way, discovered years earlier by microlensing and then confirmed by astrometry. Not the supermassive black hole at our galactic center, not a bright X-ray binary screaming with hot gas, but a dark, isolated remnant, roughly 10 times the mass of our sun, 10 solar masses. In the language of gravity, that number matters. It sets the scale of everything that follows. The event horizon, the boundary beyond which light itself cannot return, would be only a few dozen kilometers across for a black hole like this. Small on a map, immense in consequence. And around that boundary, space and time do the thing that makes black holes worth traveling to. They bend, they slow, they tilt. The mission architecture document called it Project JIBH in its earliest drafts. Inside the crew, it became something simpler, the journey. Not because it would be poetic, because it would be literal. A journey across the gradient between ordinary time and time under deep gravity. The ship was designed like a tool. No wings, no glossy hull, not a needle meant to look fast. A long, functional stack, built in orbit, because the mass could not be lifted in one piece. At the forward end, a habitat cylinder, about 8 meters in diameter and 12 meters long. Not large, but thoughtfully packed. A ring-mounted treadmill and bicycle, a small galley, 2 sleeping pods, a hygiene compartment that recycled water aggressively, a small greenhouse rack, not to feed the crew, but to keep their eyes on something alive. Behind the habitat, a thick radiation and micrometeoroid shield. It was a layered sandwich, outer Whipple bumpers for debris, hydrogen-rich polymer slabs for galactic cosmic rays, boron-doped layers for neutrons, water tanks placed strategically, because water is a decent shield and you need it anyway. Behind the shield, the spine, a truss full of cables and conduits and coolant lines. The spine held distance between the human volume and the engine volume, because the engine volume was not gentle. At the aft end, propulsion modules. Not one engine, 3. Each one meant for a different phase. The core was a staged fusion system, a pulsed magneto-inertial fusion drive. Not the kind of fusion that makes electricity in a neat building on Earth. The kind that uses a compact fuel pellet, compresses it with electromagnetic fields, and lets the plasma expand into a magnetic nozzle. Deuterium and helium-3 were the favored reaction mix, mostly because it produces fewer neutrons than deuterium-tritium. Fewer neutrons means less activation, less long-term radiation in the structure, less need to replace half the ship after every burn. But helium-3 is rare, so the budget included years of mining in the outer system, scooping it from the atmosphere of Uranus and Neptune. It was slow work. It felt like the mission was being built by weather. The second propulsion system was beamed power, a laser and microwave array in the outer system built over decades. It could put energy onto a receiver on the ship, not to push directly like a light sail, but to run high-power electric propulsion without carrying all the propellant energy on board. The ship carried a superconducting coil system, a magnetic sail, a loop of field that could interact with charged particles. In interstellar space, there are not many charged particles, but there is the interstellar medium, and the ship could also release a stream of ionized propellant to make its own working medium. A hybrid, a compromise, a way to brake without needing to bring all braking propellant from home. The third system was for the quietest part, when you are close enough to a black hole, when the gravity gradient is steep, when you want to adjust your trajectory by meters per second, not kilometers per second. You do not want pulsed fusion pushing you like a heartbeat. You want whisper thrusters, cold gas and high-ISP ion thrusters, precision control, with a propellant budget measured in kilograms, not tons. The ship had an onboard AI, not a personality, not a friend, a system, a long-duration autonomy stack, navigation, life support monitoring, fault detection, comms scheduling, radiation forecasting. The crew called it Kestrel because it hovered, because it watched, because it would not panic. There were 2 humans, not because 2 is safer, but because mass matters, because every kilogram of life support is a kilogram you cannot spend on shielding or propulsion, because the mission was already on the edge of feasible. Commander Lena Qureshi, pilot, systems engineer, trained in long-duration habitats, and Dr. Matteo Sato, relativistic astrophysicist, instrumentation specialist, missions scientist. Their training included years in centrifuge habitats to adapt to intermittent artificial gravity, long isolation runs with comms delays, radiation event drills, manual star tracker navigation with simulated failures, psychological training in slow, repetitive environments. The black hole target was labeled BH-10C, a mass estimate 10.2 solar masses, spin uncertain, maybe slow, maybe moderate. The mission assumed a Kerr black hole with dimensionless spin parameter A around 0.3, not extreme, not a near light speed spinner, but enough to make frame dragging worth measuring. Frame dragging, a phrase that sounds like fabric. It is. In rotating space-time, the rotation of mass drags the local inertial frames. It makes the geometry swirl. It makes orbits precess. It makes clocks behave differently depending on direction. The plan was not to cross the event horizon. It never was. No heroic sacrifice. No romantic plunge. The plan was to approach down to a safe periapsis, close enough to see strong field effects, close enough to measure lensing and redshift and timing, and then swing out again. Even that required care, because black holes are patient. They do not need to chase you. They let you fall. The mission was structured in phases. You can feel how engineers love phases. Phases are how they make the infinite manageable. Phase 0, construction and fueling in the outer system. Phase 1, departure and acceleration. Phase 2, cruise. Phase 3, braking and approach. Phase 4, near-field science arc. Phase 5, departure and return of data. The crew heard all this in a briefing room in a quiet orbital station, a room with sound dampers, a room designed so that the voice does not bounce. The briefing lasted a year, not in one sitting, in hundreds of hours, in simulations, in revisions, in the slow formation of familiarity. When Lena and Matteo signed the final set of mission rules, one of the lines was underscored: no schedule pressure near periapsis. Another line: no heroics. And another: assume comms silence during critical arcs, because signals travel at the speed of light, and this mission would go far. Even within our own galaxy, far is far. The communications plan was layered, a high-gain dish for laser comms when geometry allowed, a lower-rate radio system for redundancy, a store and forward buffer with error-correcting codes, a strict time-tagging system because time would not be the same everywhere. The ship carried an optical atomic clock, a lattice clock, stable enough that it could detect gravitational potential differences as a shift in tick rate. It was both a navigation instrument and a science payload, because time dilation was not just a theory to be tested, it was a condition to be lived in. In the training, they practiced saying it aloud, not as a slogan, as an orientation. Mission time is what we measure on board. Earth time is what the rest of humanity will experience. In deep gravity, our hours may be their days. They ran examples, over and over. Example 1, mild cruise. At 0.2 C, special relativistic time dilation is small but noticeable. Gamma Hansion 1, Jacques SQRT11, Vida 2 task C2. At VIMM 0.2 C, gamma is about 1.0206. That means for every 100 hours on board, about 102 hours pass for a stationary observer. 2 hours difference. Not dramatic, but enough to matter for precise scheduling. Example 2, fast transit. At 0.6 C, gamma is 1.25. For every 100 days on board, 125 days pass at home. 25 days of difference. Now you can feel it. Example 3, deep gravity. Near a black hole, gravitational time dilation stacks on top of velocity time dilation. Close to the event horizon, the factor can become large. Not infinite for you, not while you are moving freely, but significant. The mission did not plan to hover. Hovering costs infinite energy near a horizon. You cannot hold station just above it without absurd thrust, so the plan was a flyby, a plunge and swing, a carefully chosen geodesic arc. In a flyby, your proper time is finite. You experience minutes and hours. Far away, others may measure longer. They trained with the simplest metaphor. Imagine a river. Near the banks, it moves slowly. Near the center, it moves quickly. Time is like that. Gravity makes a current. Near the black hole, the current runs deep. And then they went back to spreadsheets, to power budgets. Power. It was always power. The habitat needed baseline electric power, life support pumps and fans, CO2 scrubbing, oxygen generation by electrolysis, water recycling, thermal control loops, computing, lighting, communication. The average baseline was about 20 kilowatts. Peak loads could hit 60 kilowatts during exercise and comms. The science payload needed bursts, high-rate imaging arrays, spectrometers, interferometric timing systems, particle detectors. The propulsion needed megawatts, so the ship carried a compact fission reactor, not for thrust, but for steady power, a high-temperature gas-cooled reactor, a few megawatts electric, radiator panels extended like dark wings, not to fly, but to glow quietly in infrared. Waste heat is the constant companion of space travel. In deep space, you cannot dump heat into air. You can only radiate, so the ship had radiator area that looked excessive, but it was necessary. The crew learned to listen to the ship, radiator pump vibrations, the gentle whir of a fan, the quiet click of a valve. When everything is working, the ship sounds like a sleeping machine. And then, on a day that did not feel ceremonial, Phase 1 began. The journey left the outer system with a slow push. The fusion engine pulsed at low frequency, building velocity over weeks. Not a single dramatic burn, a patient climb. In the archive record, this is the moment the story begins, not with a countdown, with a sustained, deliberate acceleration. Because the black hole would not come closer, the ship had to go. And as the ship went, so did time. On mission day 30, Kestrel delivered a gentle notification. It spoke in a calm, neutral tone. Time comparison update. Mission elapsed time, 30 days, 00 Estimated Earth elapsed time, 30 days, 1449. Differential, plus 114 hours, 49 minutes. 14 hours, not much, but a first ripple. A small reminder that the journey was not only across space. Lena wrote in the log, in plain text. Because plain text survives. We are leaving home at one rate and arriving at another. I can feel it only because the numbers tell me. Otherwise, it feels like any other day. Matteo wrote, relativity is like humidity. It is always there. You notice it when it changes. In the quiet archive, we keep these lines, because later, when the numbers grow, it will help to remember. This is how it started. Chapter 2, The Long Cruise Through Thin Dust. Cruise is not nothing. Cruise is a sequence of small tasks repeated until they become a rhythm. If you are listening and your eyes are heavy, let the repetition be comforting. The ship reached its planned cruise velocity by mission month 6. Not the near-light speeds of fantasy, a plausible, hard-earned fraction of c. The target cruise was 0.3 c. At 0.3 c, gamma is about 1.048. For every 100 days on board, about 104.8 days pass for Earth. A difference of about 4.8 days per 100 days. Not dramatic, but over years, it accumulates. Kestrel made it a weekly report. A small ritual. Time comparison update. Mission elapsed time, 210 days. Estimated Earth elapsed time, 220 days. Oro 2018. Differential, plus 110 days. Oro 2 hours, 18 minutes. 10 days. In 7 months. Lena would read it. Matteo would nod. And then they would go back to their checklist. The checklist was long. Inspect radiator panel temperatures. Check superconducting coil health. Run fusion injector calibration. Exercise. Inspect water reclaim filters. Replace CO2 scrubber cartridges. Calibrate star tracker. Run inertial measurement unit bias correction. Review micrometeoroid impact sensor logs. Record crew health metrics. In interstellar space, there is dust. Not much. But at 0.3 c, even a grain of sand carries enormous kinetic energy. So the ship carried a forward dust shield, a layered system, a thin sacrificial bumper, a cloud of ejectable micro-pellets released ahead of the ship to pre-shatter incoming particles, a magnetic field configuration to deflect charged dust. Most of interstellar dust is neutral. Magnetic fields do not move neutral grains directly, but the ship also carried a thin plasma curtain. It ionized the space in front of the shield with a low-power electron beam. This made more of the incoming material interact electromagnetically. Not perfect, but better than nothing. Every few weeks, Kestrel would schedule a dust weather session. It would map the local interstellar medium density by measuring impacts and plasma interactions. The data fed into a risk model. The risk model was a quiet voice in the background. It never shouted, it only changed colors. Green, yellow, occasionally orange, never red. During cruise, the mission was not aimed at the black hole directly, not like a straight line. In the galaxy, the black hole was moving. The sun was moving. The ship was moving. The target was a point in a moving coordinate system. Navigation was a dance between inertial measurement from gyros and accelerometers, star tracker updates, pulsar timing, pulsar navigation. A concept that feels like listening to a lighthouse in deep space. X-ray pulsars emit remarkably regular pulses. By measuring the time of arrival of pulses from multiple pulsars, you can triangulate your position. The ship carried an X-ray detector array. Not huge, just enough to time pulses. Matteo loved these sessions. He would sit in the habitat with a small screen and watch the pulse profiles. It was like watching a heartbeat, a distant, stable heartbeat. If our clocks drift, the pulsars tell on us, he said. If our position drifts, the pulsars tell on us. They are honest. They do not care where we are. They just keep time. Kestrel would respond. Pulsar timing residuals are within tolerance. Estimated position, uncertainty. 120 kilometers. Confidence, high. 120 kilometers. In interstellar space, that is a needle's width. The ship also listened to Earth, not in real time. At 0.3 C, and with the distance growing, messages took months to arrive. At the farthest point of cruise, the one-way light time would be measured in years. This is where the quiet archive tone becomes practical. Because when a message takes years, there is no urgency, there is only patience. The crew recorded video messages. They encoded them with strong error correction. They sent them in bursts when the beamed power array had line of sight. They received messages too. Old news. Familiar faces older by months. A holiday greeting that arrived after the holiday. A birth announcement that arrived after the child could already crawl. Lena found that the delay did not feel like loss. It felt like living in a different season. They are still there, she said. We are just out of phase. Matteo wrote another note. Com's delay is a kind of time dilation you can feel. The physics time dilation is quieter. The human time dilation is loud. The ship's life support ran like an ecosystem, not fully closed, but close. Oxygen was generated by splitting water. CO2 was removed with a regenerable sorbent, heated to release CO2, vented or stored. Water was reclaimed from humidity, urine, hygiene, with multi-stage filtration and catalytic oxidation. Food was mostly packaged, high density, long shelf life. The greenhouse rack provided fresh greens occasionally and helped with trace gas balance, trace gases. The invisible part of living in a sealed volume. A whiff of ammonia from a cleaning mishap. A faint solvent smell from a repair. A slow build-up of formaldehyde from plastics. Kestrel monitored it all. Trace gas analyzer, nominal. Ethanol, 0.3 ppm. Ammonia, below detection. Formaldehyde, 0.01 ppm. Lena would inhale gently. The air always smelled like clean machinery. Warm polymer, and faintly, like people. Radiation was the constant concern, not because it was dramatic, because it was cumulative. Galactic cosmic rays are high-energy nuclei. They pass through shielding and create secondary particles. No practical shield blocks them completely. So you reduce exposure, you schedule, you shelter. The ship had a storm shelter, a small compartment near the water tanks. If a solar particle event arrived, they would retreat there. In cruise, solar particle events were less relevant. They were far from the sun, but cosmic rays remained. Kestrel kept a dose budget. It was like a bank account. It did not care about feelings. Crew dose update. Lena, 0.42 SV cumulative. Matteo, 0.39 SCV cumulative. Forecast to periapsis. Within limit if shielding schedule maintained. Sieverts, a unit that feels too abstract. But Lena learned to translate. It means our risk goes up, she said quietly. It means we do not take unnecessary exposures. It means we do not do spacewalks unless we must. During cruise, they did one maintenance EVA, not because they wanted to, because a micrometeoroid had punctured an outer bumper layer, not the pressure hull, just the sacrificial shield. But it needed repair. They waited for a low-risk window. They cycled the airlock. They stepped out. Space at 0.3 C is still. No wind, no sound. Just the faint vibration through suit structure. They worked as slowly. They used adhesive patches and bolt-on plates. They checked for secondary cracks. Back inside, Lena wrote, EVA at this speed feels like standing on a moving train in the dark. You cannot see the motion, but you remember it with your bones. As the years passed, the crew's bodies changed subtly. Even with exercise, muscles maintained mostly. Bones carefully monitored. Vision watched for pressure changes. Sleep managed. They used a circadian lighting system. Blue-rich in the morning, warm in the evening, dim at night. They used sound. A library of quiet noise, soft fans, rain recordings, and always Kestrel, a calm narrator. The ship's trajectory was a long curve. The black hole was not a point you aim at and hit. You aim at the space it will occupy years from now. By mission, year 5. Earth year 5 plus a little. Kestrel reported, mission elapsed time, 5 Ozuru years. Estimated Earth elapsed time, 5.24 years. Differential, plus 0.24 years. About 88 days. Matteo smiled. 3 months ahead of us, he said. Home is always a little ahead. Then he turned serious, and later, home will be much farther ahead. Because the approach phase would involve acceleration and braking, higher velocities, and then gravity. The black hole was still a dim starfield coordinate, but the instruments began to sense it, not directly, no light. They sensed its influence. As they approached, the star positions shifted slightly due to gravitational lensing. In the data, background stars bent around an invisible mass. A black hole is known by what it does to light around it. Matteo ran the first lensing fit on board. He plotted the deflection angles. He compared to general relativity. It matched. Within uncertainty. We are not there yet, he whispered. But spacetime is already leaning. And on another weekly report, Kestrel added a new line. Gravitational potential estimate at current range. Negligible for crew time dilation. Dominant time dilation, kinematic. Not yet, but soon. The long cruise ended the way it began, not with a fanfare, with a scheduled burn. Phase 3, braking and approach. The ship turned, not in an instant. Over hours, a slow rotation using reaction wheels and thrusters. Then the fusion engine began to pulse again. But now it pulsed opposite the direction of travel. A braking burn. At the start of braking, the ship's velocity relative to the black hole's local frame was still high. As the ship slowed, it spent less time dilated by speed, but as it drew deeper into the gravity well, gravitational dilation grew. Time dilation is not one thing, it is layers. Lena recorded a simple explanation in the audio log. There are two ways our time changes. One is because we move fast. The other is because we are deep in gravity. They both make our clock run a little slow compared to far away. We are trading one for the other. In the quiet archive, we keep her voice, not as drama, as clarity. Chapter 3. The approach where light starts to lean approach began with numbers. Then it became sensations. Not sensations in the skin, but in the instruments. The black hole did not brighten. It remained dark, but the space around it became busy, not with visible gas. This black hole was isolated, no bright accretion disk like the ones in popular images. But nothing is perfectly isolated. There is always some gas. There is always some dust. As the ship approached within tens of astronomical units, then within one, then within a fraction, Kestrel began to show new overlays, gravitational lensing map, predicted photon trajectories, safe periapsis corridor, tidal gradient warnings. The mission planners had chosen a periapsis distance based on tidal forces. Tidal force is the difference in gravity from one part of your body to another. It is what stretches. Spaghettification is a vivid word for it. For a black hole, tidal acceleration roughly scales like Chartius 2 gm such L R3, where L is the length of the object, say a human body, and R is distance from the center. For a stellar mass black hole, tidal forces near the event horizon are intense. For a supermassive black hole, the horizon is huge and tidal forces at the horizon can be gentle. This mission went to a stellar mass one, so the safe distance had to be larger. They would not go near the horizon. They would go near the innermost stable circular orbit, ESCO, for their assumed spin. No, they would remain outside it. ESCO is the smallest radius at which a stable circular orbit exists. Inside that, orbits become unstable and plunge. For a non-rotating black hole, ESCO is at 6 gm on mean 2, which is 3 times the Schwarzschild radius. For 10 solar masses, GM-NC2 is about 14.8 kilometers, so 6 GM-NC2 is about 88.8 kilometers, and the horizon is at 2 GM-NC2, about 29.6 kilometers. So for Schwarzschild, horizon, Shears is 30 kilometers, photon sphere at 3 GM-C2 is 44.4 kilometers, ISCO at 6 GM-C2, 88.8 kilometers photon sphere. A radius where light can orbit, not stably, but it can circle. The mission periapsis was set at about 500 kilometers from the center. That is about 17 Schwarzschild radii, far outside the photon sphere, far outside ISCO, still deep enough to measure strong gravity, still close enough to see gravitational redshift and lensing vividly. At 500 kilometers, the gravitational time dilation factor for a stationary observer relative to infinity is SQRT1 RS char, where RS just 29.6 km, R chart 500 km, RS R 0.0592, SQRT1 0.0592, 0.970. So a stationary clock there would tick at about 97 point the rate of a faraway clock, a 3% difference. The ship would not be stationary, it would be moving fast at periapsis. That adds velocity time dilation. The combined effect on their proper time compared to far away could be roughly several percent more. Not a million, not a movie, but enough that over hours, the difference becomes minutes. Over days, hours, and the deeper passes later, if they dared, could be more. The first approach pass was conservative. A demonstration, a systems check, a way to make sure the navigation solutions matched reality. Navigation here was not just stars, It was curvature. The ship used star trackers, but star fields were distorted. Pulsar timing, but pulses were gravitationally redshifted. Laser ranging to autonomous beacons deployed ahead on inbound trajectory. Those beacons were small, mass of a suitcase. They carried atomic clocks and transponders. They were deployed in a line like breadcrumbs. The ship would ping them, measure round-trip time, correct for known relativistic delays, Shapiro delay, a time delay for signals traveling through curved space-time. Near a massive object, light takes slightly longer than it would in flat space. Matteo explained it in a log intended for future listeners. Imagine you walk across a room. Now imagine the floor is a deep carpet. Your feet sink. You still go straight, but it takes longer. Light is like that near mass. The space it travels through is deeper. The beacons also served as a reference frame, because near a black hole, you cannot just assume an inertial frame the way you do in deep space. Everything is falling, everything is curving. The ship's engine was mostly silent in approach. It used the magnetic sail occasionally, interacting with a sparse plasma and its own injected ions. It used ion thrusters to adjust. Kestrel handled continuous navigation updates. Trajectory solution update, periapsis 502 km, plumb 1.2 km. Confidence 0.92. Tidal gradient forecast at habitat centroid, within structural tolerance. Radiation environment, low. Radiation environment. Near an accreting black hole, radiation can be intense. X-rays from the disk, jets. But this black hole was quiet. Still, there was something. A faint, hot halo of gas, a weak accretion flow. At low accretion rates, the flow is radiatively inefficient. Most energy goes into heating ions and outflows, not bright light. The mission carried particle detectors. They saw low-level proton flux, occasional electron bursts, a faint background of high-energy photons. Not dangerous, but measurable. Lena and Matteo spent their evenings in the habitat watching the star field, not with eyes, with a display. As they approached, the star field began to distort. Stars near the black hole's direction shifted. Some appeared doubled. Some formed arcs. Gravitational lensing is a gentle thing until it is not. At one point, Matteo pointed to a ring. Einstein ring, he said. A background star nearly aligned. The black hole is making a circle of its light. He did not say it like a spectacle. He said it like noticing a pattern in snowfall. The ship's camera array was calibrated to measure these distortions precisely, because from the distortions, you can infer mass, and from subtle asymmetries, you can infer spin. Spin. If the black hole rotated, frame dragging would shift the lensing pattern. In Kerr spacetime, the ISCO depends on whether you orbit with the spin or against it. Prograde orbits have smaller ISCO, retrograde larger. The plan included 2 flybys, one in a prograde geometry, relative to estimated spin, one retrograde, measure differences. But first, one conservative pass. As the ship approached within a few thousand kilometers, Kestrel began to schedule time tags differently. Time system note. Gravitational potential is increasing. All science timestamps will use onboard proper time with conversion table to barycentric coordinate time. Barycentric coordinate time. A reference used in solar system ephemerides. Here, adapted. Matteo explained to Lena, we keep our own clock, but to compare with Earth, we need a coordinate time. The conversion depends on our path through gravity and our speed. Kestrel will maintain the mapping. Lena nodded. So, even our timestamps have to travel, she said. They slept in shifts, not because the ship needed a human awake, because it calmed them. In the hours before periapsis, Lena woke. She floated to the forward observation screen. She watched the lensing map. There was no sound, but the geometry felt loud. Kestrel spoke. Approach to periapsis, 03.12 Inksmile. Current range, 12,800 kilometers. Relative velocity, 0.08 c. 0.08 c, not their cruise. They had slowed, but not enough that speed-time dilation vanished. At 0.08 c, gamma is about 1.032. Small, but at periapsis, velocity would rise due to gravity. In a flyby, even if you were braking overall, the local speed near closest approach can be high. Gravity converts potential energy into kinetic. They were falling. But falling is the natural state. In free fall, you feel weightless. You do not feel gravity, you feel tidal forces. The ship was designed to handle those. At periapsis -1 hour, Kestrel reported predicted time dilation factor relative to far field at periapsis, 0.945 to 0.962, depending on velocity profile. Expected Earth time advance during periapsis hour, 62 to 64 minutes per 60 minutes on board. A quiet sentence. But the meaning is clear. For an hour they experience. Earth experiences a little more, 2 to 4 minutes more. Not magic, not a century, but real. Lena recorded, I am trying to imagine 2 minutes. It is not much, but it is the beginning of the slope. Matteo replied, relativity is not a cliff, it is a hill. We are walking down it. Then the ship crossed the last breadcrumb beacon. It pinged, it received. The response arrived with a delay slightly longer than expected. Shapiro delay. Matteo watched the plot. There it is, he whispered, space-time making signals late. And then, periapsis. The ship did not shake. It did not roar. There was no sensation of passing a boundary. But the star field on the display did something unforgettable. The blackness at the center did not remain a simple dark disk. It became a region where the background wrapped. Light from behind the black hole bent around. Some photons took paths that looped partially around before reaching the camera. You could see multiple images of the same star at different positions. The camera system recorded it all. Spectrometers measured redshift, gravitational redshift. Light climbing out of a gravity well loses energy. Its wavelength stretches. It becomes redder. At periapsis, the ship measured the spectrum of a background pulsar that passed near the line of sight. The pulses arrived slightly shifted, slightly delayed. Matteo smiled like someone hearing a familiar song played in a new key. The ship's atomic clock was the steady heart. It ticked. It did not care. But later, when they compared it to the coordinate model, it would tell the story. The ship swung past and began to climb out, not with thrust, with trajectory, a gravitational assist, not to gain speed, but to change direction, to set up the next pass. In the hours after periapsis, Kestrel delivered a summary. Periapsis pass complete. Onboard elapsed time during closest approach window, 02 Giaco. Estimated far field elapsed time, 2.07 to 30. Differential, plus 100 to 07 to 30. 7.5 minutes in 2 hours. Lena exhaled. It was not fear, it was awe. 7 minutes, she said. Home moved 7 minutes ahead while we did 2 hours. Matteo nodded. Now imagine doing it deeper, he said. The mission plan did include a deeper second pass. Not reckless, but closer. Next periapsis would be 200 km, about 6.8 Schwarzschild radii. Still outside photon sphere, still outside ISCO, but much deeper. At 200 km, RSR pumped 0.148, SQI1 0.148, 0.9, a 7.7% gravitational factor for stationary. Combined with higher speed, the total could be around 0.85 to 0.9. Now the difference per hour becomes several minutes to over 10 minutes. The slope steepens, but before that, rest, calibration, review, because the quiet archive does not skip the in-between. Chapter 4. The second pass, close enough to taste the gradient. The second pass was planned like a piece of music. A slow approach, a precise timing, crescendo, a release. Between passes, the ship coasted on an elliptical trajectory. It went out to a safer distance, then fell back in. During this time, they processed data, they checked systems, they rehearsed contingencies. Contingency A, loss of star tracker due to lensing confusion. Solution, rely on IMU and pulsar timing. Contingency B, radiation spike. Solution, shelter, reduce electronics exposure, pause science. Contingency C, thruster failure. Solution, adjust plan, accept higher periapsis, abort deeper pass. Contingency D, navigation divergence. Solution, fire correction burns earlier, use beacons, accept data loss over crew risk, no heroics. The deeper pass required a small engine maneuver at apapsis, not large, a few tens of meters per second, but precise. Ion thrusters fired for hours, a soft push, the ship's trajectory shifted. Kestrel reported the resulting periapsis prediction. Updated periapsis, 201.3 km plus, 0.9 km. Closest approach time, mission day, 2193, 14 in 22, ton. The ship's structural model predicted tidal stresses. The habitat cylinder was aligned along the radial direction to reduce torsion, because tidal forces pull along the line toward the black hole. Better to have the strong axis aligned. In the last days before the pass, Lena and Matteo practiced moving into the storm shelter quickly, not because they expected a solar storm, but because it was the most shielded volume. If something unexpected happened, if an energetic particle burst appeared, that was where they would go. They stored water bags around the shelter walls. They added food packages. They checked the medical kit. In the quiet tone of archive, the details are soothing, because preparedness is calming. On the night before periapsis, Lena lay in her sleeping pod and listened to the ship, the fans, the pumps, the distant hum of the reactor. Kestrel's voice was low. Reminder, periapsis science sequence begins in 08:00. Crew wake schedule in 6:00. She slept, not perfectly, but enough. Matteo woke early and drank warm water. He floated near the instrument bay. He checked the spectrometer alignment. He checked the photometer calibration. He whispered, half to himself, "We are going to watch light circle." He was thinking of photons near the photon sphere. They would not be at the photon sphere, but they would see higher order lensing, light that had wrapped around more than once, faint but present. As the ship fell in, the black hole's influence became stronger, not in a pull you could feel, in how the displays warped. Star trails were not straight. Kestrel used ray tracing models in real time. It predicted where stars should appear, given the ship's position. Then it compared with observed. Then it corrected the navigation solution. This is what autonomy means. Not a personality, a relentless model-fitting engine. Lena and Matteo strapped into seats near the shelter, not because acceleration would be large, because in a high-attention window, you want your body stable. Kestrel announced, range, 3,100 kilometers. Relative velocity, 0.12 c. At 0.12 c, gamma is 1.0073, still small. Then, range, 1,000 kilometers. Relative velocity, 0.18 c. At 0.18 c, gamma is 1.0166. Then, range, 400 kilometers. Relative velocity, 0.5 c. At 0.25 c, gamma is 1.0328. Velocity time dilation, about 3.2%. Gravitational factor at 200 km for stationary, about 0.923. Combined, their proper time relative to far field could be around 0.89. Kestrel translated in a way that humans can hold. Expected Earth time advance per onboard hour during periapsis window, approximately 67 minutes per 60 minutes, 7 minutes per hour. Now you can feel it, not with skin, with imagination. Lena spoke quietly. So, if we are close for 3 hours, Earth gets 3 hours and 21 minutes. Matteo nodded. And if we were close for a day, Earth gets a day and almost 3 hours. He paused. And if we were close for 10 days, Earth gets 10 days and more than a day. They did not plan 10 days, but the arithmetic mattered. It made the abstract tangible. As periapsis approached, the ship began to see a faint structure, not a bright disk, a dim, asymmetric glow in radio and infrared, a low-rate accretion flow, gas captured from the interstellar medium. Not much, but enough to form a tenuous disk. The disk's inner edge was not sharp, but the data suggested a temperature gradient, hotter inward. The spectral lines were broadened, partly by thermal motion, partly by Doppler shifts. Doppler near a black hole is intense because orbital velocities are high. Material close in can orbit at a significant fraction of c. When material moves toward you, its light is blue shifted. When it moves away, red shifted. Combined with gravitational redshift, you get an asymmetric line profile. Matteo watched the line profile and felt calm, because it matched the textbooks, because reality was behaving. Then the lensing map sharpened. The black hole's shadow, not a physical surface, a silhouette against the background. The shadow size is related to the photon sphere. For a Schwarzschild black hole, the shadow angular radius corresponds to about 2.6 rs. They could not resolve it with the naked eye, but with interferometric baselines between ship cameras, with careful calibration, they could reconstruct it. The shadow was not a perfect circle. If the black hole had spin, it would be slightly distorted. Frame dragging would shift photon trajectories. This was the heart of the science. Not romance, measurement. At 10 minutes to periapsis, Kestrel said, tidal gradient across habitat, 0.12 G difference end to end, within comfort threshold. 0.12 G difference, not nothing. It means your head and feet would be pulled differently. But in free fall, you do not feel weight. You feel stretch, a gentle tug. Lena said, I can feel a little tension in my spine, like someone pulling my ankles softly. Matteo replied, that is the gradient. That is the black hole saying hello. Periapsis. The instruments ran their sequence, a timed choreography, high-speed imaging at multiple wavelengths, spectroscopic sweep of the dim disk. Pulsar timing passes behind the black hole to measure Shapiro delay and lensing, atomic clock comparisons, gravitational wave antenna check, not expecting detection, but monitoring. The gravitational wave antenna was a set of long baseline laser links along the ship's truss, a tiny interferometer, not LIGO, but sensitive to local strain. They did not expect a merger, but they wanted to measure any background. During periapsis, the clock data was the simplest. The onboard clock ticked. Kestrel recorded its phase relative to a far-field model. Lena watched a simple display. 2 lines. One labelled ship, one labelled far. The far line moved slightly faster. A quiet proof. Matteo whispered, later, in a moment that was not for the log, we are really doing this. He said it once. He did not repeat it. It was not a slogan. It was a quiet alignment. The ship passed through periapsis and began to climb. In the hours after, Kestrel reported, closest approach window on board, elapsed time, ZO3 Zuvura. Estimated far-field elapsed time, ZO3.2110. Differential, plus 100 to 21:10. 21 minutes in 3 hours. Lena leaned back. She smiled, not because of thrill, because the universe had offered a measurable gift. So if we did this for 30 hours, she began. Matteo finished. Earth would get 33 and a half. And if we did it for 300 hours, Lena continued, Earth would get about 335, Matteo said. They were practicing again, making the numbers into something the mind can hold. But they would not linger. Lingering would be dangerous. In the days after the second pass, the ship's trajectory carried it out, away from the deep well. The lensing distortion softened. The star field became more familiar, but the data remained, stored, backed up. And the time mapping table in Kestrel grew longer, a record of how their clock had slipped relative to Earth. By the end of the black hole's science arc, Kestrel estimated, total differential accumulated since mission start, 0.38 years, Earth over mission proper time. Almost 5 months. Lena imagined Earth 5 months ahead. Not much, but a quiet reminder. Matteo reminded her, 5 months is the difference between winter and summer. In a mission, seasons are not weather. They are messages. They are faces. The return of data would take years, even at light speed. So they began the long work of compressing and prioritizing. Science data triage, a careful act. Raw imaging stored in redundant, solid-state arrays. Keyframes selected for immediate downlink. Spectrometer datasets compressed with lossless methods. Clock and timing data duplicated in multiple formats. They also prepared for departure. The ship still had to escape the black hole's neighborhood. Escape does not require infinite energy, only enough to climb. The magnetic sail was used as a brake earlier. Now, it could also act as a slow accelerator by interacting with plasma streams. But the plasma density was low, so they relied on fusion again. A burn, a staged burn, weeks of pulsed thrust. And as velocity rose, again, kinematic time dilation returned. Kestrel resumed weekly reports. Mission, elapsed time, 6.10 years. Estimated Earth elapsed time, 6.58 years. Differential, plus 0.48 years. Almost half a year. They were leaving the black hole behind, but they carried its imprint, and the mission entered its next quiet stretch. Chapter 5. The return that is mostly waiting. Return is not a reversal. It is a new journey with a different kind of patience. The ship was heavier than a data packet, so it did not return to Earth quickly. It returned the only way it could, on an arc, with long coasts, with careful use of energy. The mission's primary goal was data, not a human homecoming. The crew could return if the ship remained healthy, but the mission accepted that the crew might end far from Earth, not as tragedy, as realism. Lena and Matteo understood this. They had accepted it. Still, return felt like pointing the bow of a boat toward a familiar shore. Even if the shore was decades away, they sent the first major data packet within weeks of the second pass. It was a summary, key results, a preliminary mass measurement, a spin estimate, a reconstructed shadow image, clock drift curves. The laser comm system fired in tight beams. It was like speaking through a straw. Precise pointing. Kestrel controlled the pointing using star trackers. It used guide stars not too close to the black hole direction, because lensing still distorted the field. The first packet took years to arrive. That is how space works. In the meantime, the crew lived. Life support continued. Maintenance continued. The reactor required periodic control rod adjustments. The radiator panels required inspection. The fusion drive required injector cleaning. The superconducting coils required thermal cycling to manage trapped flux. The ship's consumables were counted: food, spare filters, medical supplies, replacement circuit boards, sealants, lubricants. The mass budget had included redundancy, but not infinite redundancy. So they treated every part gently. They also treated themselves gently. They had learned that the mind in deep space does not want constant stimulation. It wants rituals. They had rituals. Morning, exercise, then warm drink, midday, maintenance tasks, afternoon, science data review and system checks, evening. A short message recorded to Earth. Night, dim lights, quiet sound library. They read books, they listened to music, they watched old films. But their most consistent entertainment was the universe. During cruise back, they continued to run physics experiments. Because a long mission is an opportunity, they used the atomic clock to map gravitational potentials along the trajectory. They tested the equivalence principle by comparing clock behavior with accelerometer readings. They monitored cosmic ray flux in different regions of interstellar space. They also practiced explaining time dilation, because they knew that when the data arrived, Earth would ask, what did it feel like? And the honest answer would be, it felt like a ship. It felt like a schedule. It felt like being alive far away. But they could still offer numbers. At mission year 8, during a high-speed cruise segment, Kestrel estimated velocity at 0.4 c. Gamma at 0.4 c is about 1.091. Time comparison update, mission elapsed time, 8.0 years. Estimated Earth elapsed time, 8.77 years. Differential, plus 0.77 years. About 9 months. Lena said, so Earth is 9 months ahead. If someone left a message today, we would see it in... Matteo checked the comm geometry. Another 6 years, he said. They laughed softly, not bitter, just acknowledging the scale. Comm's delay had grown as the distance increased, even as they turned back. When you are far from Earth, turning back does not make the light time shrink instantly. You have to travel back before the distance closes. So for a while, the delay continued to grow. Then it plateaued. Then it slowly decreased. At the maximum, one-way light time was around 12 years. That means a question sent from Earth would be answered 24 years later. So Earth did not ask questions. Earth received reports. The crew wrote like archivists. They described the lensing. They described the clock differences. They described the moments of quiet. They also described the risk. Near periapsis, the ship had measured tidal flex. The truss had flexed by millimeters. Sensors recorded strain. The data would help future designs. They had measured a small but consistent frame-dragging signature. Not dramatic. A precession in the orbit of their deployed beacons. A subtle asymmetry in lensing. Matteo wrote, the black hole is not just mass. It is mass with memory of rotation. The geometry remembers. Kestrel, ever literal, appended spin parameter estimate, A, SHA 0.28 Panpla, 0.05. They had measured gravitational redshift in the faint disk lines. They had measured Doppler boosting. They had reconstructed a shadow. All of it would arrive on Earth as delayed light. On board, the most immediate manifestation of black hole physics was the time mapping table. Kestrel maintained it in a simple file, a list of segments. For each segment, start proper time, end proper time, estimated far-field coordinate time interval, uncertainty. In quiet moments, Lena would open the table. She would scroll. It was like a diary written in 2 languages. At mission year 10, Kestrel reported, total differential accumulated. Plus 1.12 years Earth over mission, proper time. A year. Now it was tangible. Matteo said, if we had a friend on Earth who sent a message on our launch day, and if we could read it instantly, it would be from a year later than what we have lived. Lena replied, so, our launch anniversary on Earth happened a year ago. Yes, he said, and to Earth, we are older by our own clock, but their calendar has moved more. She nodded slowly. We are time travelers by paperwork, she said. The ship continued. There were problems. No mission of this length is smooth, but they were solvable. A coolant pump began to vibrate. Kestrel flagged it. Pump 3 bearing wear trend increasing. Recommends swap within 90 days. They swapped it. They used gloves. They worked in slow motion. They cleaned connectors. A CO2 scrubber sorbent bed degraded faster than expected. They adjusted the regeneration cycle. They reduced metabolic load by shifting exercise times. They ate slightly less on heavy maintenance days. A section of radiator developed micro cracks. Kestrel detected a small pressure drop in a heat pipe. They isolated the segment. They deployed a spare panel. Each fix was a small story, but always quiet. The return phase included a planned magnetic sail deceleration in the outer solar system. The magnetic sail concept is elegant. A large loop of superconducting wire creates a magnetic field. The field interacts with charged particles in the solar wind. Momentum exchange. A break. In deep space, the solar wind is weak, but near the sun, it is stronger. So the plan was to arrive on a hyperbolic inbound trajectory and use a combination of magnetic sail interaction with solar wind, beamed power from the outer system array, a final fusion braking phase. Beamed power on return would be easier because the infrastructure was in the solar system. The beaming array could track the ship. It could deliver megawatts, but not constantly, because pointing matters, because diffraction matters, because the beam spreads. The ship's receiver was a large, thin structure, a rectenna for microwaves, a mirror for lasers. It could fold, it could deploy. When it deployed, it looked like a pale flower. Kestrel scheduled beamed power sessions. Beam power window in 12 days. Expected delivered power, 18 mem-hours for 6 hours. Use, battery recharge, ion propulsion, data transmission. During those windows, the ship's systems felt more alive. Fans sped up, radiators warmed, transmitters hummed, and the crew would send a burst of data. They knew Earth would not see it soon, but sending was still a relief. One day, Lena recorded a message. If you are hearing this, it means we succeeded in keeping the ship alive. It means the data made it through. It means you are standing on Earth, in a gravity that feels ordinary, while listening to people who spent time near a black hole. I hope you feel calm when you hear this. Her voice did not carry drama. It carried steadiness. Time dilation continued to accumulate, mostly from velocity now. At 0.4 c for long stretches, the gamma factor is 1.0091. That means about 9.1% difference. Over 10 years, that is nearly a year. Combined with the black hole passes, their accumulated difference grew. Kestrel at mission year 12. Mission elapsed time, 12 Onsul years. Estimated Earth elapsed time, 13.42 years. Differential, 1.42 years. A year and 5 months. Lena said, somebody who was 12 when we left is now 13 and a half. Matteo replied, and we are 12. He paused. But our bodies are 12 with cosmic rays. They checked their health. Bone density, stable. Muscle, maintained. Eyes, mild changes. They were older, not in calendar, in experience. The ship approached the region where the heliosphere's influence began to matter. The plasma density increased. The magnetic sail had more to push against. The deceleration began, not as a sudden slowdown, as a slow surrender of speed. And as the ship slowed, kinematic time dilation decreased. Kestrel's weekly time reports changed. The differential stopped growing as fast, but the accumulated difference remained. It is like interest. You cannot unearn it. When the ship finally reached a stable solar orbit, when it could transmit at high rate, when the beamed power system could support sustained comms, Earth began to receive, not messages, history, and the crew waited. They waited for acknowledgement, but acknowledgement would arrive years later, because now Earth was behind in light time. Even as they approached home physically, the information lag remained. It is an odd asymmetry. You can be near home and still far in time. In the quiet archive, we do not dramatize this. We let it be what it is. The crew prepared for the final phase. Chapter 6. The data arrives, and the clocks tell the truth. The last phase of the mission was not a landing. It was a handoff. The journey did not dive into Earth's atmosphere. It could not. It was not built for that. Instead, it entered a high, stable orbit around the Sun near the outer system. A rendezvous point. A place where a future crew or automated tug could meet it. A place where its data could be harvested in full. The immediate priority was downlink. The ship used lasercom to a network of receivers, large telescopes, adaptive optics, error correction. The first complete dataset to arrive on Earth would not be the most dramatic image. It would be the timing data, because timing is hard to fake. Because the atomic clock had traveled, the clock had kept its own rhythm, and the mapping table had recorded its drift relative to far-field coordinate time. When Earth received the clock data, scientists would compare. They would fit models. They would look for deviations. General relativity predicts precisely how clocks behave in gravitational fields and at velocity. Any deviation could point to new physics. But even if there was no deviation, measuring in the strong field regime is valuable because it tests the theory where it has not been tested much. The ship's near-field imaging would provide another anchor, a shadow reconstruction, a lensing map. Earth had imaged the supermassive black hole M87 Cas and Sagittarius A using the Event Horizon telescope, but those are supermassive. Their timescales are different. Their horizons are huge. A stellar mass black hole changes quickly, but it is also much smaller and harder to resolve. The journey's advantage was proximity. It could sample the field directly. It could measure curvature not only by distant imaging, but by local clock and trajectory. One of the most valuable data sets was the beacon precession. The deployed breadcrumbs had traced geodesics. Their orbits and drifts encoded the space-time geometry. Matteo had processed the data on board. He had derived a preliminary spin, but he knew Earth would do it with larger teams. He recorded one final explanation of frame dragging. If the black hole rotates, space itself is not just curved, it is twisted, like water in a whirlpool. If you try to orbit, the whirlpool pulls your orbit around. We measured that pull as a slow turning of the path. Lena recorded an explanation of gravitational redshift. Light is like a coin you spend to climb. If it climbs out of deep gravity, it pays energy. It comes out stretched. That stretch is redshift. We saw it. They also recorded a more human explanation of time dilation. We did not feel time slow. We felt days and nights. But our clock and Earth clocks disagreed. The disagreement was not a glitch. It was the geometry. They offered concrete examples, because the mind holds examples. Example, during the second periapsis window, their 3 hours corresponded to about 3 hours 21 minutes far away. They experienced 180 minutes. Earth experienced about 201 minutes, a 21-minute difference. Example, during the long cruise at 0.4 C, for every 100 days on board, Earth experienced about 109 days. So after 1,000 days on board, Earth would have experienced about 1,091 days, a difference of 91 days. Example, total mission differential at the end of the black hole arc was about 5 months. By solar system arrival, it was about 1 to 2 years. They said it softly, not as bragging, as accounting. The final onboard summary included Hawking radiation. Because people always ask, Hawking radiation is real in theory, but for a 10 solar mass black hole, the temperature is tiny. The Hawking temperature scales like T H bar 1 3, 8 pigm kb. For a solar mass black hole, it is around 68 Kelvin. For 10 solar masses, it is about 69 Kelvin. That is colder than the cosmic microwave background. So the black hole absorbs more radiation than it emits. It will not evaporate on any human timescale. The evaporation time scales like M3. For stellar mass black holes, it is vastly longer than the age of the universe. Matteo recorded, "If you wait for Hawking radiation here, you will wait longer than galaxies last. Our black hole is not dying. It is sleeping." That line was kept. The last months on board were quiet. The crew had done their close approaches. They had survived. They had collected data. They had returned it as light. Now they lived in maintenance. The ship's systems were designed to last. But nothing lasts forever. Lena and Matteo began to prepare the ship for possible future occupants. They organized spare parts. They catalogued failures. They wrote procedures. They also did something personal. They recorded a sound library of the ship, the fans, the pumps, the quiet click of relays, because one day someone might listen and feel calm. And then, at last, acknowledgement arrived. Not a live conversation, a packet. A message from Earth sent years earlier. It contained a simple thank you, confirmation that the first datasets had been received, preliminary validation that the clock data matched general relativity within error, a request for specific raw segments. The request was old by the time it arrived, but it did not matter. It meant Earth was there. It meant Earth had listened. Lena read it slowly. She said, "They heard us." Matteo closed his eyes. "Then the journey exists in 2 times now," he said. "Our time and theirs." Kestrel, ever steady, added, "New instructions received. Scheduling downlink of requested segments during next beamed power window." The mission continued, not as a dramatic finale, as a sustained archive. In the end, the ship's time mapping table showed the full differential. Mission proper time elapsed from launch to solar orbit insertion, 14.2 years. Estimated Earth elapsed time, 15.9 years. Differential, published 1.7 years. A year and 8 months. They had traveled, they had watched light bend, they had measured clocks, they had lived. And if you are listening now, remember that the universe does not need to be loud to be immense. A black hole is a simple solution to Einstein's equations. It is also a real object. It has a horizon. It has a photon sphere. It has an ISCO. It has tidal gradients. It has frame dragging if it spins. It is a place where time behaves differently. But the crew's days were still days. Their meals were still meals. Their sleep was still sleep. Even when far away, life remains made of small things. The quiet archive keeps those small things, because the details are the bridge between awe and understanding. Because when you hold the details, you can relax. You can let your breathing slow. You can imagine the ship, long and slender, radiators glowing faintly. You can imagine the black hole as a dark center that warps the star field. You can imagine two clocks, one on board, one far away, drifting apart by minutes, then hours, then months. And you can imagine the gentle truth that physics is not a story device. It is the story. This was a quiet archive story, where the story ends.